And thanks for the opportunity to talk here. What I'm going to talk about is the AI-based design approach. If you think about the design approaches, I'm just going to specifically target the complex systems or the systems which take a long time to design in the design process. This can be because of too many complex stages. It can be because of too many humans involved in the loop, right? There's a lot of information exchange. But it can also be because of the tools which you use to analyze the process and to make do the decision-making process. All those can combine lead to very time-consuming process. This kind of problem is very relevant to Siemens because we manufacture one of the most complex systems in the world, which is the large gas turbines. We also manufacture a lot of simulation softwares, or the design software, which goes in the process of creating those kind of designs. So it's very relevant to us. If you think about it, the large gas turbine can take anywhere from 6 months to 10 years in the design process, depending upon the size, depending upon the needs. So we talk with our business units, and we try to start tackling this problem about 3-4 years back, looking at the new approaches, also looking at the advancement with the technologies bringing from the hardware side, but also in the area of machine learning and artificial intelligence. So how can we make our software more intelligent? How can we make the design process much simpler? Well, not much simpler, but easy to use by the design engineers who are not the domain expert in that area. So we started this about 3-4 years back. We started to develop certain frameworks, and I'm going to talk about that framework, a big kind of a highlight, and some use cases which goes along with that. So before going into that, I wanted to show this cartoon, and probably some of you might have seen it. It's from the systems engineering side. It's basically kind of shows the gap between intent and outcome, right? So if you think about it, a customer may basically want to explain a swing which he wants, and he explains in a fashion which is shown in the rightmost corner. But then you can see what happens at various stages. The information get lost, and because of human in the loop, also what you end up getting is very different from what he wanted, and even the customer may itself doesn't know what he wanted. He may have wanted something as simple as that. So the point is that there's always a good intention when you start the design process, but what you eventually get may something slightly different or very different, depending upon how do you do the various tasks in the design process, and how do you address them. So with the machine learning tools, we not only want to do automation, but also make intelligent decision process, and so we get what we intended for. So the outline of my presentation, I'll just give a brief overview of the concept which we are working on for last 2-3 years, which is the generative engineering for design. And then I will talk about some of the core technologies within that framework, which goes along towards development of that kind of framework for application to different use cases. And then I will talk about a couple of use cases from 2 different areas where we try to put together these technologies in order to address certain issues. And finally, I want to just put in a slide various research issues which, from my point of view, from Siemens' point of view, which we see, which still need to be addressed. And that's why folks over here, it will be very, it will be good if you guys can take on those topics and try to address those issues, so that we can then take those algorithms or methods you develop into commercial software. So. Okay, so before going to talk about what our view of generative engineering or generative engineering for design is, I just want to briefly touch on what is the current design process. If you look at the current design process, it broadly in three steps. The first step is define, and define is the requirement, defining the requirements, defining the problem, or formulating the problem in such a way that you can start to process the information. Second stage is create. So that's where you start to create solution. And that's a step which takes a lot of time, basically because, especially in the complex system or complex parts where you have a lot of design engineers, they basically try to come up with what you call seed designs or initial design based on their knowledge which they have in their mind, the tacit knowledge. Also based on what kind of design process they have done in past on the similar product, and they try to utilize that to come up with new design, kind of a variant design, and then try to tinker with that to come up with more solutions. And the last stage is basically then they evaluate all these solutions. And if you're lucky, you get the right design right away, but that's probably never the case. What you end up doing is that the design which you generated may not be meeting certain requirements, or may not be good enough for what you like. So you then basically start to iterate this process, and you go through this iteration several times. Now, one thing I'd like to point out here is that this iteration loop is not like a optimization iteration loop, but it's rather the loop which the human engineers goes through the whole process. If you think about a gas turbines which is made of thousands of components, each components are being designed or tinkered with when you want to come up with the holistic design. And there's a big loop which goes. So one loop like that can take several actually months. So that's what happens in the real scenarios. And in the end, what happens is that either you used up all your time, which is allocated to basically do the design, or you have used up all your dollars. So what you basically choose is the design which kind of almost meets your requirements or meets your requirement, may not be optimal, and you move forward with that. And in the end, what ends up happening is that in reality, you are focusing on one design and just trying to tinker with it so that it meets all your requirements. And other issue is that many a time in this kind of design process, the domain experts are not always talking with each other. They basically do their part and forward the information. So the knowledge is siloed. There's no one person who knows about everything. So in that case, the system or the process becomes very inefficient. And usually a lot of iterations are required to achieve this. So what we want to do is basically to revolutionize the digital enterprise or this whole process by two steps. One is digitalizing the engineer and the physical world knowledge. Now, what does it mean? This overall approach which we are going towards is more knowledge-based approach, knowledge-oriented approach. What we want to do is to capture the knowledge as much as possible from wherever it can. Starting from the human engineers who have knowledge inside their head, how do you capture the tacit knowledge? Or basically the knowledge which is coming from the engineering data. It can be specification sheet or any other kind of data regarding the problem. And also, if you have made similar products in past and they have been operating in field, can you basically utilize that information to learn more about the problem so that you can do a better job at designing this process? So the first step is capture. And what you really want to achieve is that instead of you basically taking one design and tinkering it, you want to explore thousands and thousands of design in a very fast manner, but you want to discover the right design from those designs. So what we want to do is to basically capture the knowledge, and in the end we want to achieve the design discovery instead of tinkering with the design. And the way we can achieve that is basically to have this generative design engine where we use machine learning techniques to basically speed up the process of design generation as well as the analysis of the design itself. So, which is one of the big bottlenecks. So how can we achieve that the designs get generated automatically and then automatically analyzed so that the engineer who basically has his main task is more on looking at the outcoming solutions and then be able to take better decisions about what he wants and how the design should look like. Okay, let's go on. So all this work we are right now, which we are doing, which we are not doing in a black hole or anything. We have been collaborating both heavily internally with our business units, but also externally with university and other industrial partners. We are working a lot with the government agencies like DARPA or Department of Energy or DMDI on government-funded projects to basically develop modules within this generative design framework. We're also working with university collaboration, especially with Georgia Tech. I'm very happy we have a lot of collaboration or collaborative project ongoing right now. We have Dr. Paulino here and Dr. Dimitri Mavris and Lee Song with whom we have projects. We have several use cases. So it's not that we're trying to design something and apply it to one use cases. Right now, actually, we have close to 26 use cases. This is a slightly older slide. But these use cases are across, they run from turbine design to basically transformer design, to application to building technology, to grids and stuff. So basically, we're developing a lot of these use cases where we can showcase these kind of technologies, but we are also developing concepts. For example, it's very hard to see, but we are developing a framework in which you can we can build the pipeline of machine learning technologies without too much tinkering, so that you can directly apply to a problem. And this is kind of a framework we want to give it to our design engineers, so that they don't need to know exactly about how this algorithm is going to work, or how do I hypertune the parameters, or tune the hyperparameters, sorry. So it becomes easier for them to use. We're also developing a lot of technologies, apart from just the machine learning and AI-based tools. We're also looking at digital memory, which what it means is that when we are running these use cases, it's generating thousands and millions of data, right? How do you actually how do you store it in such a fashion so that you can use it later on? So we are working on concept as to efficient storage of these results. We are working on autonomous simulation and validation, which is basically how do you develop techniques so that the simulation itself gets automatically created with the right parameters. And so you can run it automatically and then do the validation process also automatically. The other aspect we are looking is the more intuitive and interactive system for what-if trade analysis. So what it means is that, especially if you think from the design engineer point of view, you give him a piece of software and you ask him to trust it. But while he's using it, he wants to be part of this design process. So how can you basically build the tools where the engineer is also involved in the design space exploration process, and they can directly utilize their knowledge about the design itself. So you basically direct the design process in a specific direction in the design space. We're also building tools for more efficient design space exploration, which is basically when you are generating thousands and thousands of solutions, what is the best way you can present those to the design engineer? How can they explore these different solutions? Not only looking at several of them, but also if they want to go deeper and look at one design in a lot more detail, how can you bring up the properties which is most important to him, right? And then we are developing these reusable components, which is basically that lot of algorithms which we develop, we don't want to customize it to a specific use case, but it has to be a generalized framework so that we can implement them across these different problems. We are taking all these technologies we develop to a different maturity level, more towards TRL 7, 8, and then we want to hand it to our business unit, who can then take the various technologies, algorithms, and methods and approaches we have developed and implement in the commercial software which Siemens provide. So this is the last slide on the generative design side, but I just wanted to go over a little bit more detail about what we mean. So this is, as I said, I just showed earlier that we have 3-step process in the generative engineering side, which is capture, explore, and discover. So in the capture side, we are working on trying to basically build up these distillers which take the raw data and then convert into knowledge modules. So whether the raw data is coming from engineer at work, what it means is that how do you capture the engineer's tacit knowledge? You're not going to go to the engineer and ask hundreds of questions and basically take the answer and build a rule base. What we want to do is to basically build up techniques where the technique or methods which can monitor the software which the engineer is interacting with, and then capture those set of actions in the form of knowledge modules. So for example, we did with our NX that we build plugins which can monitor all human actions or interactions with the software tool and then automatically convert that into a knowledge form. We want to also have distiller which can look at the engineering data from the past design data and then extract all important features about those past designs, those information, and then build up a knowledge module out of it. The third is basically, if you start to go towards a design process, the first thing you get is a huge requirements document. This thing should do this should not, violate this, and so on and so forth. How can I take that document and directly convert into a form of a knowledge or knowledge graph, or in some form in mathematical equations directly, so my objective functions or constraints are getting formulated from that design, from the requirements document. We also want to look at the past data about a product which has been in operation and extract information for that. So once we have all this knowledge, how do we represent it? And that's a big key, that you want to have a representation which the machine learning tool then can use those kind of representations. So in most of the use cases where we are following this process, the knowledge base we're using is basically knowledge graphs. And when we take all this knowledge and then construct this knowledge graph for each of the individual use cases, which kind of embodies everything about that problem of that specific use case. Once you have all this knowledge, what we want is that we want to explore design, right? We don't want a human to basically start creating initial design, but we want to have some kind of methods which will start to generate lots and lots of seed designs, which or synthesize these design, and then be able to run simulation in an extremely fast manner using surrogates to basically quantify that particular design in terms of certain KPIs or certain metrics. While this process is going on, if you think about it, there's also knowledge generated in this analysis process, right? So how do you extract the knowledge and then bring it back to the knowledge graph which you have? So and in order to do that, once this new knowledge is getting added, you still want to use the knowledge in this design process back again. So for that, what we need is some kind of explorer which is dynamically adding the knowledge and then utilizing that knowledge and bringing it back in the design process itself. So we built several tools to basically do that process. Now once this this design process is going on and is being quantified, the design engineer who's basically either watching the process or getting the output of this whole effort, you're generating so many design solutions. What you want to eventually provide is the insights about these designs. So whichever designs come out as a successful solution, what features you can extract and present to the user in what form, so that he can take important or efficient decision. So in our process, we have built this kind of framework, but also tools for each one of the yellow box which you see, and that's what we have applied to different use cases. Any questions till now? I mean, I can take questions, that's fine. Okay, I'll continue. Okay, so now let me talk about the core technologies. So one of the core technologies as I talk about is the knowledge and the knowledge graph, which we are using in our case to basically represent all that knowledge. Why knowledge graph? There are several reasons. You can read, but I want to just highlight the one which are in black outline. So one of the key things which we found out with working with different problems is that if you represented the knowledge in a knowledge graph form, you can easily discover hidden or contextual information from this knowledge graph. As you add more and more knowledge, as you have more nodes getting generated, you will discover a relationship which was not there in one instance, but it may be in the other instance. But as you add more instances about it, these entities or these relationships will automatically emerge, which will help you in your design process. Another big advantage we learned is that it's very easy to extend and merge new knowledge. I'll give you an example. So we were using knowledge graph to do subtractive manufacturing. So we will build this whole huge knowledge graph about what are the different resources, what kind of capabilities they can have, what kind of operations they can do, what are the skills they can provide. And we basically, we use that knowledge graph to come up with the most optimal way of manufacturing, let's say, a part, right? And then we come up with, okay, what if we have to add the knowledge about additive manufacturing, right? And in that case, it was very easy. We just added a subgraph with the similar schema and then make the connections, and it was it. That's it. And all the algorithms didn't need to actually change. So then we can do hybrid manufacturing, right? We can utilize the knowledge graph to do, how to make a part both using additive and subtractive machine. And that was actually a fun project. Another aspect is that it's hard to see, but what it says is that easy to discover higher level information. And basically the idea is that you can, instead of using knowledge graph as a full scale, you can also do graph of graphs, where the node becomes a subgraph. And when you start to do that, you will start to see information and pattern at a different scale, and learn about the system and part, which you can then utilize for your problem solving. So this kind of shows some examples of the knowledge graph in different use cases we have. So Bob generation simply means bill of process generation. What is the correct sequence or most optimal sequence of process which you want to follow in order to create a part, in order to manufacture a part? So we use knowledge graph to basically embed the knowledge about the manufacturing process and the design, and then you utilize that. NX Advisor, again, it's very hard to see, but it's actually based on a project which we are doing with Georgia Tech with Professor Dimitri Mavris. And the goal was that as the user is interacting with NX, how can the knowledge dynamically gets created, and then utilize this knowledge to do a prediction of what user wants to do next. And if he selects that that's what he wants to do all those steps automatically. So this, and then we have hybrid manufacturing, as I talked about. The goal there was basically that if you have both subtractive and additive machines, how can you manufacture a part using combination of these machines, right? So we basically embed all the knowledge into what we call design graph to achieve that. In the architecture exploration, it's more of a 0D kind of analysis where you want to explore the architecture at the architecture level about your system of systems, right? So for example, a suspension system can have several components, and you want to know what kind of components should be in what combination, which leads to a successful suspension. So we use graph embedding based approach to basically do clustering to see what are the areas in the design space which leads to successful combination, leading to a successful architecture for suspension. And last but not the least is the data storage. So we're running so many use cases. We have so much data, and for each use cases we have different kind of problem and scenarios. What we found is that we can store the data. You store all the data about the solution and the problem in a knowledge graph such that we can learn about the problem and solution across different use cases. So you can characterize the problem in a certain way, you can characterize the solution in a certain way also, and then you can store the solution, for example, the weights of the neural networks and everything in these knowledge graph, and then if you get a new problem, you can find the similar problem there, and then try to find out what kind of machine learning tools I can use, because the similar problem have this kind of machine tools, so machine learning tools. So this is just few example of the knowledge graph. This is a bill of process generation use case, and I'll talk more about it, so I'm going to skip it. This is just shows more detail about it, that various types of node, what are the design feature nodes, what were the manufacturing feature nodes, and the relation and the process nodes, and how you can know that this manufacturing feature can be realized by a certain process, and all this was embedded in the knowledge graph. So this is the next advisor knowledge graph, where each node has information about is basically the representation of the state of the NX software while the user is making an action. So edge is basically the action made by the user, and node is basically the state of NX software, which is a design tool. And each node will also encapsulate all the information about the features and geometry with respect to that state in NX. And this actually gets generated completely automatically as the user is interacting with the design software. Let me skip that. Okay, so this one is the knowledge graph which we utilize for the hybrid manufacturing use case, where the goal was that given a CAD part and given a set of resources, what kind of subtractive and additive operation I should take to basically come up make this part. So we embed the design into a kind of a design graph, where each node is basically the manufacturing feature and edge of the surface, and then utilize this graph to basically come up with the most optimal operation, because each of those manufacturing feature can be done additively as well as subtractively, and there's a certain cost associated with it. So we use these kind of graphs to basically explore what kind of set of sequence of operation which leads to the least amount of cost, and are the solution for basically manufacturing these kind of parts. So this is basically different kinds of distiller which we have developed for converting the raw data into different kind of knowledge graph. This is more on the components which can be used across the different use cases, and they require minimal amount of customization. So all of them have algorithms which are independent of the problem, but then you can customize the interfaces such that you can change the schema on one of the end and be able to generate different kind of graphs from that raw data. So just very quickly, when we are talking about knowledge in knowledge graph, what is the new knowledge in the knowledge graph? So it can be anything among these or all of them. It can be a constraint, which is derived from the past data, which, for example, you may learn that certain action can not be performed in front if another action has preceded it, which that's what we find out in manufacturing use cases. But also it can be new relationship between entities, as I showed earlier. For example, you find out that you have to do CMM before drilling, right? You want to position where your laser pointer where you want to drill, and then you can learn that kind of relationship as you input a lot of data or take the past data. It can be in the form of generation of new entities, which basically means new kind of nodes, or also it can be a combination of several rules or several edges which occur together, and basically you look at the topology of the knowledge graph and try to find similar topology in the other knowledge graphs. Or it can be new solution itself. Once you add the new solution in your knowledge graph, it brings the new knowledge along with that solutions. So this is just an example of what it means to basically have a new knowledge. This was the knowledge graph part of the knowledge graph which I showed earlier. And what ends up happening is that this red edge is not there, but as you start to add more data, you start to learn that a certain operation is always followed by another operation, and which means that in my solution later on, if I add this operation, then I should also add the other operation also. And so you can learn these kind of things from the data. Okay, so next part of the core technologies are the surrogate models. So we have used several methods. This is just an example of one method. We use deep residual network as a forward model in many of the use cases. Where the goal is that, okay, you want to have the design parameters, but you want to quickly predict what is your KPI or the metrics. So we applied we have applied it to a lot of use cases, where this is one of the use cases which is on the power printed circuit board. So we are basically trying to build up filters and we want to analyze filter in extremely fast manner. So what we want to know is that, given a certain design parameters, which can be resistance or capacitors in that filter, what will be the gain and frequency? So we basically, and this just showed that once we develop this surrogate models and apply our data to it to basically do this kind of prediction, we get a very high degree of accuracy using those ResNets. So these are more common form of surrogate model, which I think you guys already use. But one other interesting thing which we started to use was also the inverse model. So the forward model is a very common form of surrogate models. But inverse model, what we want to do is that, given a certain output, what are the possible inputs? So for example, if you look at the forward problem, the goal is basically to predict y given an x, and in that case, any kind of deep network will work very fine. But if you invert the problem, where you have been given y, but you want to predict an x, if you take neural network, it will be very hard for neural network to generalize this problem. So we basically try to look into different techniques to solve this problem. Here we just show one, which is mixture density network, but we also use other techniques like GANs to basically do the same job. But the idea there is that instead of to basically generate the surrogate model or inverse model for this extremely nonlinear map, what we want to use is Gaussian functions. So so basically you can select a set of Gaussian function, and the goal basically becomes that you want to learn from data the mean and the variance of these different Gaussian functions, such that you can basically estimate the input given a certain number of output. And then we applied the same problem to the printed circuit board or the filter problem, where there was a certain desired gain and frequency, and then for all those desired gain and frequency, I can estimate what different set of design parameter or design solution which can be generated. And you also get the amount of accuracy, amount of what is the probability of this design to meet the desired gain and frequency requirement. And it also gives you the information about, for a given design, which are the parameter it is most sensitive to. So it's kind of a local sensitivity information which you directly get from these kind of analysis. Now this is basically, how do we put all these things together? So you have forward model and inverse model. But now you want to use them in a combined fashion to basically do an optimization, which is machine learning driven optimization, which is the key part to our design space exploration process. So if you look at a general regular way of traditional way of doing an optimization, what you end up doing is that you start with some cold initial design, which is then what you call as seed design, and then you basically generate lot of seed designs or designs around it, and then you basically analyze them through some kind of a simulation or a simulation analysis tool or some kind of a surrogate model, and then you basically have a certain stopping criteria. And if your stopping criteria is met, you get a final design. Otherwise, you keep on doing this, performing this loop till you meet this criteria. So the idea is that maybe can we invert this process? So instead of starting from a cold design, what if we start with a design target, right? So we have our inverse model. We can start with a certain target. It can generate, instead of generating a cold initial design, we can generate hot initial design, which have a high probability of meeting the design requirements. And then basically you do small perturbation around those hot design points to find out if I'm able to get an optimal design. Since there is also this is using forwards and inverse model which have some kind of uncertainty in their prediction, so you will never. It's very hard to say that you got an optimal design, but you need to have a certain criteria to make a decision whether you want to stop at a certain point to say this is my most improved design, or else you can use that design as a starting point for the traditional optimization algorithm. And that's what we realize is that if you combine the traditional optimization algorithm with some kind of machine learning optimization, you can cut down the design, or at least the design optimization in a significant manner. And this is just a heuristics of which we utilize to basically do the exploration, which basically we inverse and inverse model generates the design solutions, and then we take these seeds and do perturbation in the local design space to do certain evaluation loop and find the best design. Okay, another aspect is also on the dependency and causality analysis. So basically, one of the things is that when you're doing this design process, very early in the stage, you want to know for a given design, which is meeting your requirement or not meeting your requirement, which are the parameters which are most responsible for the design being in a certain state. So you want to do some kind of dependency or causality analysis. What we at least implemented for now is some partial correlation based approach to do the influence analysis, which is basically in the given network, I can find out which are the parameters or in my system, whether input or output, which are most influential. So what are the most influential nodes in my design, which affects a certain output? Or I can also know which are the nodes which are most influenced by the other parameters. So basically, I can do something analysis like this, where we are doing a CFD analysis, and we want to do a prediction about success of the CFD simulation. And in that case, we also want to know which parameter are responsible for this success or not. So we can do this kind of analysis to look at certain input parameters, and the size basically kind of tells you like how much it's contributing towards the simulation success. And that way you get an idea that when you want to change your CFD simulation parameters, what changes you should make and where you should make those changes. So I like to go towards some use cases where we have applied all these technologies. First use case is in the turbine design process, where we applied that machine learning based optimization approach. So this is just a traditional approach where you have design experts who start with certain design parameters. They have some kind of aerodynamic analysis tool which gives them some engine performance, and they use that along with traditional optimization tool to do the design process. And it can be very time consuming and labor intensive. Oops. Yeah, and so what we did was basically, instead of that design process, we applied the machine learning based optimization approach, which I showed you earlier, and we went from requirements to the design parameters, and we use this forward model and the inverse model in the loop to basically come up with a new design. So either that design can be suggested as a design, but it can also be then fed into some kind of a traditional optimization approach to find more optimal design. And this was the actual problem which we looked into. So this is what you see, the design parameter and different KPIs. And for the forward model, this is for the inverse model. And this is some of the results which we were able to get. So we compared our results with Heat's software. This is optimization software or multidisciplinary optimization software. What you see here is that in our method, first we ran Heats for 50 iteration, and what we were able to get as an efficiency value was 65.98. We applied our machine learning optimization approach. We ran about 100 iterations for 30 seconds. What we got is still pretty far. But then we took this design point as an input and provided to this software, to the Heat software. And within 1.1 minutes, we were within 11 iteration, what we were able to achieve was a much better solution than what Heat's got on its own. And so that's one of the power of using this machine learning based optimization, is that okay, they may not give you an optimal solution, but they can give you a very good insight into what can be the initial design point which you start your optimization with.
Just a question. Where would you get the training data for your inverse model? And how many examples could you have?
So that's a good question. So for this one, the data we got was from actual turbine use case. We have about 13,000 training set data for that. The more, the better it is, and so there is a training time also required for that. But once you have these kind of models, you can use it for different purpose and different optimization issues. Yeah. Okay, so this is the last use case, which is bill of process generation. So when we are doing design process or exploring the design, we are also looking at design of the production process. So what is the best way to manufacture a certain part, or what is the best way? What is the most optimal bill of process which can be generated to manufacture a certain turbine or blades or vanes? So this is the use case we did with our power generation group, where what happens is that you want to design a blade, and you want to have a blade with a new feature, which is diskpleknut. It kind of means slot, I think. And in reality, what happens is that they have a lot of information about the past data, like in past how this blade was created, and the blade was created by a certain steps, number of steps, which is a bill of process. This is an example of the bill of process, where all the steps are there, and then all this is done manually. So it's a human engineer who basically goes and say, okay, we should do this step, and the text is written here. And so it's a human written text. This whole process is completely manual. So the problem is that, okay, can we somehow automate this process? If we have a lot of data about how a turbine blade with a certain manufacturing features was manufactured in the past, can we learn from that and be able to automatically generate the bill of process given new sets of requirements? So that was a problem. Okay, this is some. So so in reality, you get certain requirements, the product owner, and then you basically contact your domain human experts or design experts. They basically interact with themselves as well as the tools to basically create this what we call routing. So how do you route the different process? And also these steps are not all in one factory. They are across several factories inside a city or across the cities. So it's a very complex process, and it takes a lot of time, where you have the results. What you get goes to the ERP system, then the routings are created, and then they are sent to the production site for actual implementation. But you want to avoid this. This is very kind of time consuming, and there's a lot of information and a very inefficient way of doing it. And what we want to actually achieve is that somehow be able to extract the knowledge out of the past data and centralize this knowledge, so that the user is just looking at the outcome solution to make a final check, rather than in the process trying to decide what is the best bill of process to basically achieve the goal. So the approach we followed was three steps approach. First, as I said, was basically capturing the knowledge, and capturing the knowledge about how an engineer in the past has gone in various steps to basically come up with the steps to manufacture a specific part. So that is that aspect the engineer has done from his own mind, from the past experience. So that data contains the tacit knowledge of the domain expertise of that human engineer. So how can we capture that? Once we have captured, we want to utilize that to basically automatically then generate the new routing for a new blade or new vanes which I want to manufacture. And then the last stage is that once you've generated these steps, you still want to make sure that you have to validate that outcome to make sure that it works in the real world scenario. So to capture the knowledge, we had about 65,000 sheets like this, and this is a very small one. But a lot of times the process column, which is a human entered information, had a lot of spelling mistakes. They use different words for the same meaning, and so there's a lot of and you want to somehow automatically extract all the knowledge from these sheets. So what we ended up developing was a natural language processing based distiller, as well as different kind of machine learning classifier, which basically reads all this information, takes the information, information in this column, and then tries to classify each word into product, process, or resource, and then learn what steps are creating which manufacturing feature. So in the end, out of those 65,000 Excel sheets, what we learned was that, okay, if you want to create a feature A or feature B, these are the 10 different ways or 100 different ways of manufacturing it. So we learned the mapping between manufacturing operation, and the manufacturing feature. And all this knowledge basically gets stored in the knowledge graph which we had. Once we have all that knowledge, then once we get a new problem where the goal is basically to have this new feature in this turbine blade, the first goal is that basically, given this problem, what is the closest similar problem from the past, and how do you basically determine that? And that is what we call a variant. So we basically were able to get a base design automatically, and then generate a variant of that, which is the new design. So this is the process where basically you load a base design which you have determined, and then select the features which you want. And once you add the new feature, what the search algorithm does is that it tries to basically take that feature and learn and take the past data of how many different ways this feature can be created, and then what is the most optimal way of basically adding these new steps in the existing process. So you end up with something like this, where this is the three different way of manufacturing the same turbine blade with new feature. This is a base design, and these are the steps which are automatically learned from the knowledge graph, and they can be added either at this step, or a different way of doing it is basically just two-step process, two different operations, and adding somewhere there, and at different locations. So you can generate several of these kinds of solution, and but you want to basically validate them or select which one is the best one. In this case, all the operation comes with the operational time, like how much time it takes to basically set up the process, and how much time it will take to do the operations. And so the goal was simply that what is the least amount of time it takes to basically manufacture the part. And then we basically validated this generated solution over a different software called plant simulation, where all these processes can be implemented, and then you can automatically implement it, and then basically you can see if I want to manufacture 100 parts, how much time it will take, or in a week how many parts I can generate, and then select the best solution. Okay, so that's almost close to my presentation. For the future direction point of view, the things which I thought will be quite useful to look into still, and we are looking into, but it will be great for you guys to look into too, is that some of them are listed here. One is, the first one is the interactive design space exploration. So given a lot of time what happens is that the human design engineer, they have certain idea about this is the kind of design they want, but they cannot quantify in mathematical equations. But they can select certain designs. how can we make this whole process interactive? How can you learn the tacit knowledge or the what's called bias inside the human mind to basically, which is there regarding certain design. The second is design space characterization, and there's a lot of work still there, but it's already done. But can I just from the data infer very quickly which are the portion of design space which are good, bad, or which contain certain specific features? Third is basically automatic constraint on design rule generation. So this is basically if you got a lot of data about the past, both input and output. I'm not looking at just a parametric relationship, which you can probably derive, but also higher level knowledge about in terms of which can be explained in natural language form. Can you derive something like that? Automatic formulation of objectives for your optimization problem, right? Given the requirements, given let's say past information on how the past problem objective functions were, can you automatically form the objective function and also the constraints for that objective function? Automatic surrogate generation. So this is one of the projects which we just started with Professor Dimitri Mavris, but the goal is that a lot of time you can't expect the design engineers to be a very good knowledge about machine learning tools. You want to at least have a process or tools which they can then use and generate these surrogate model. If you don't do that, they will never use these kind of tools ever. So the idea is that make their life easier. So given a set of data, how can I generate surrogate model which basically does the tuning of hyperparameter automatically, right? So how do you capture and utilize human bias, right? So a lot of time there's a bias in the design engineer's head, and then how do you capture those kind of bias so that you can show proper designs to him? Design for designers intent. This goes towards the first, the cartoon which I had was that how can we make sure that whatever was the designer's intent, can I capture that? Can I really understand the intent and what he actually need, and then utilize that? Parametric mapping across scale. So when you do design for complex systems, you basically have 0D, 1D, 2D, 3D, right? And then you have parameters all across these different dimensions. Can you automatically link those parameters in such a way that if I make change in one of my dimensions, I can clearly right away see possible changes with a certain probability in my other dimension, let's say 3D, right? If I change my shape in the 3D side, can I automatically see the change in my requirement side? So how can we do that? Automatic knowledge capture from requirements document. This is work which we are currently doing also, but it's extremely complex process which requires not only NLP but learning the relationship between the various portions of the document itself, which and the features which are described in those documents. Also, time evolving knowledge for design version control. So a lot of times in these complex things, there's lot of versions of designs are generated. Can you capture this knowledge in the knowledge graph, but which is time evolving, right? Right now, you have the entities and relationship in a static manner, but can we do a temporal aspect also? Transfer learning for cross-domain or cross-physics design problem. So can you use the knowledge which is solved for one problem, can you utilize there? And it's a very traditional transfer learning problem, but in practicality, it's very hard to use and very hard to generalize. And then last but not least, which algorithm to choose when? I mean, given a problem, which machine algorithm should I use and why? Or, and so I think with that. Oh, yeah, of course. So in our group and in general in Siemens Corporate Technology, we are always looking for bright talents. We are hiring right now, and we will be hiring a lot more in the areas which are mentioned here. So if you are expert or if you have knowledge and if you want to work further and do research in any of these topics, please contact me or Livio or Jan here. And I think that's it. Yeah. Thanks.
So I had a question about the turbine example. It looked like you'd optimized 20 or 30 variables, but how do they get translated to full turbine design?
Okay, so this is just one problem. We have a lot more use cases related to turbine, which looks at different, not only just, that was just an aerodynamic tool, which I wanted to show. There's a lot more let's say, results we have achieved, but we cannot show it.
So,
So
I mean, if you've optimized like the 20 or 30 input variables, does that define an entire turbine design?
No, it's not.
So how do you get from that to the turbine?
So this is basically just one 1D tool in earlier stage of the turbine design process. I think what you are referring to is that if I'm doing the overall turbine design, right?
Okay.
Right. So this is going to help in, let's say, the first stage. So they spend about 3 to 4 months in trying to come up with the 1D design or 0D design of the initial architecture exploration before they start to do the CFD and CAE analysis. This is the aspect with just at that stage. This is not, once you have this tool, it will at least speed up that process. But you have to build a tool like this for all different places where they are using some more complex. In another project, which I cannot show results here, but we are looking at basically the CFD. We are trying to speed up the CFD process for, let's say, one of the components I cannot mention, but one of the components of the compressor, which is very time consuming. So, and I mean, I have results, but we just not allowed to show. So, yep, yeah.
First off, thank you so much for coming here and sharing your insights.
Thank you.
I had a quick question, especially in light of what's happening with the 737. What are your thoughts on how do you have a lot of old systems and mission critical systems like gas turbines, right? But they need to be constantly updated and so on and so forth. So you're making these little iterations. How do you always validate those things under such tight constraints? Like, so for example, on the weekend, right, I actually work at a data center. And what we've seen is, like, for example, like either it could be Dyson Crump, it could also be with simplex systems. There's certain things that happen that when they show up, they have no idea why.
Yeah.
And most times, like I said, nothing is at risk. No one is gonna die, someone might get trapped in the elevator or so on and so forth. I was really curious, like, how do you guys deal with that?
That will be probably a question exactly to my business unit colleagues, which are not here. But I know the problem which you are talking, because it's along the line of software assurance or assurance of the system if you change a small portion. And this is a big problem in the DoD side also with these aircraft, where you just make one change, but you have to go through a 5-month of certification process, even with the small change in the code, right? So it's a big issue. I'm not sure. So I think there can be several machine learning approaches, or at least not machine learning, maybe probabilistic approaches which can be applied. We have actually a project along the similar line with DARPA on the assured, it's called ACE, assured and composed evidences. Basically, we're using evidence theory-based approaches to basically study these. When you add in a complex system, if you just change a piece of code or a piece of, let's say, module, how the risk or the risk heat map changes for the overall system. So how they do it for turbine, I think I cannot answer that question from the business side, but I know that's a big issue in general. Yep.
You guys open source anything?
Oh, sorry. Yep. Open source. Yes. So some of the softwares which we developed through the government grants, they are kind of open source. So once we finish, we basically either in one case, at least I know for DARPA, there's a project which we are doing called understanding group bias, where we're trying to quantify human bias. That has a GitHub on that. But most of the use cases which are through internal, we are not allowed to. Yeah. But of course, the project we are doing with Georgia Tech and Princeton and other folks, they will be open.
So this is maybe a really high-level layperson type question, but I'm interested to see your perspectives on this. If you imagine a future in which tools and approaches like this are broadly deployed, is it your expectation that we're more or less likely to have really novel breakthrough designs? Does this approach tend more towards incremental refinement versus really sort of radical change? Or do you have any sort of feel at this point, based on your practice, what the long-term impact on overall design might be for these approaches?
Right. I think the low-hanging fruit is basically to speed up the process. There's just too much efficiencies, because, I mean, because of human in the loop and because of just the way we are using these tools, that we have to first solve those processes. But the idea is that eventually the design should be, in what we call organic, or something which a human will never think about. I'm not sure if you are, like, for example, the antenna use case. You may have seen pictures. Yeah, exactly. So that was generated through machine learning tools rather. So when a human tends to conceive a design, it's very systematic. It's very it has to be symmetric, and there are certain things which goes into it. And I'm talking right now, for example, if you're trying to design a shape, right? Topology optimization and places like that. Whereas if you go for machine learning techniques or other, they might not even think about that. They were just looking from the optimality point of view, whatever criteria you have set. So the end goal is to achieve what you said, but I think right now we are just trying to also speed up the whole overall process, which is very inefficient right now.
Thank you.
And if I can add to that point, one of the interesting aspects we discovered in some of this work, we also were able through machine learning to identify novel architectures of systems that in one particular case, they were looking at the gearboxes and the shift mechanism and so on. And they were primarily 2 to 3 architecture well known for decades and used in almost all the cars and all the vehicles out there. And we were able to actually discover a completely new one that was not patented by anybody, never even processed or reported in any publication and so on. A fourth one, let's put it this way. So it is possible.
Would consider this creativity in this situation. I mean, that's a loaded phrase.
I don't know exactly. That's a very loaded question. I don't know that.
The novelty is there.
Right. There is definitely some novelty, right, and the possibility to exploit those for that purpose as well.
All right. Thank you.
So that's interesting that you mentioned the patent process, because I'm terrified of when you just wire this thing up to legal and you can just start, shooting out patents all day long. But yet, thinking about patents as one of those, it's your due diligence to do a patent search, but, well, as part of that patent search, right, like, what can I find out about that stuff? Your requirements document becomes very interesting. Your requirements document analysis becomes very interesting when you can take other people's ideas, like literally take the knowledge. I don't think you can get sued for taking the knowledge embedded within a patent, right? That's really interesting.
I mean,
we're looking into a very interesting area now. I think there is also convergence, right? Also in the patent law, machine learning is becoming more kind of a standard nowadays, and do a lot of the analysis and quick evaluation and so on. Here is becoming, as Sanjeev showed, also in engineering. So it is an interesting direction what you are highlighting, and seeing what is it that you can actually take out and what is actually infringing and non-infringing.
Yeah.
I wish I had a better answer than just, I don't know.
Drive us around your Ferrari.